Chapter 9 is about confidence intervals. It is the most common application of stats. I already mentioned to you it's used in presidential elections to try to guess who the president's going to be, doing polling kind of thing. That was section 9.1, where you're trying to guess a percentage of people that'll vote for someone or whatever. But confidence intervals are used in all sorts of different places. Pretty much, like lots of different businesses will be using confidence intervals in some shape or form. Now, if you're the statistician working for the company, you'll be doing those things. If you're not, then you might never see this stuff. So it's used everywhere and it has important applications in real life. And we'll maybe briefly talk about a couple of those today. But let me just recap what was happening. Section 9.1, we were trying to guess or estimate P, a percentage. And to do that, I taught you how to do that, and you had to use the Z table when you were doing problems like that. In section 9.2, last class, you were trying to guess an average. Remember, these numbers, P and mu, those are numbers. Every stats problem is about a big group, and if you collect data from the entire big group, you can calculate these things, but we don't collect that data. So you imagine that data as a big imaginary bag of numbers that we haven't actually collected, and our goal is to guess these numbers. And we've learned the way to guess it with confidence intervals. And when you're guessing P, use the Z table. When you're guessing mu, use a different table, use a T table. Today, we're going to be building confidence intervals for population standard deviation, sigma. So today, we're going to be guessing sigma. I'll tell you the whole story in a minute, but we're trying to guess sigma. And we're going to be using a new table again today. So remember, on my website, if you click on miscellaneous, there's links with 4 tables, there's 4 links right next to each other. We're going to be using the 3rd table today. It's called the chi-square table. You can print it out now. Make sure you have these tables in front of you for the exam. You're going to need the Z table, the T table, and the chi-square table. So it'd be a great idea if you print it out right now, but definitely by the time you take the exam, you want to have that table in front of you. All right, so let's go ahead and get started and talk about, I'm going to tell you the story. The story that I'm going to tell you now is almost identical to the story I told you last class. It's almost identical to the story I told you in section 9.1. 9.1, 9.2, 9.3, the stories are very similar, okay? Just it's a different quantity we're trying to guess, okay? But other than that, it's basically the same thing. So one more time, here's how the story goes. Every stats problem is about a big group. Usually it's a big group of people. If you collect data from that entire big group, you can answer the question and get the answer right, and the case would be closed. But the group is so big that collecting data from the entire group is not feasible for us, okay? It might take way too much time or cost too much money to do that or whatever. So the idea is, if you don't have all the data to calculate the quantity you're trying to calculate, how do we still figure out that quantity? Okay. So this bag over here, population data, I want you to imagine that's if we collected data from the entire population, all their answers are in this bag. It's a bag of answers. Like if my population is everybody who lives in California, and maybe I want to know their average age, let's say, then imagine I talk to every single person in California and ask them for their age. All their ages are in here. How many people live in California? I don't know, tens of millions, right? So that means there would be tens of millions of numbers in this bag. But we don't have the time to talk to every single person in California and ask them for their age. So you need to pretend someone did. Someone asked every single person who lives in California for their age, put them all in a bag, and I get this huge bag of numbers that we're calling population data. But because we don't actually calculate this data, we could still imagine it though. So it's an imaginary bag of data that we wish we had, but we don't have. And what I want to know today is the standard deviation of all the numbers in the bag. We call that sigma. Sigma is a standard deviation of a big set of data that we don't have, okay? Sigma is a standard deviation. Remember, that measures how spread out the data is. Now, we're dying to know this sigma. We'll talk a little bit about why we would want to know a sigma later on. But anyway, so we're dying to know this sigma. How are you going to figure out what it is? You're going to guess at it, okay? We can't figure it out exactly because we don't have this data to calculate it. So what do? you do what you always do in a stats class. The first step in any stats problem is to take a sample. Okay, so we're going to take a sample. That means we're going to take some numbers out of the bag. Or a different way to say that is, we'll talk to some people in California and ask them for their age. Not everybody. We'll talk to some of them. And that's called a sample. And then we get a bag of numbers, another bag of numbers called sample data. What's the difference between population data and sample data? Population data is data collected from the entire big group, the group that the question is about. Sample data is data from just the people that we talk to. So this data is collected. So we have these numbers accessible. They're in front of us. We don't know these numbers. It's an imaginary bag of numbers. Sigma is the standard deviation of all these, and that's what I want to know. S is the standard deviation of these. And S I can calculate because I have this data. So sigma and S are both standard deviations. Sigma is the standard deviation of this big bag of numbers that we don't have. That's why we don't know sigma. S is the standard deviation of the small bag of numbers that we do have. So we do know S. And we use S as our best one number guess for sigma. So remember, we're trying to guess sigma. There we go. Our best one number guess is S. And I told you that first day of class. So S is our best one number guess for sigma. But the way confidence intervals work, we don't like one number guesses because they're almost always wrong. So we want an interval guess instead. And that's what we're going to be doing today. So instead of making a guess, like let's say you calculate S and it's 1.7. You're going to say, okay, I think sigma then is 1.7. It's like S is the standard deviation of these numbers here. It is 1.7 exactly. What's the standard deviation of these? I don't know. I'm guessing it's the same. I'm guessing it's 1.7. I'm probably wrong. It's probably a bad guess. So we don't want to guess like this. Is called a one number guess or a point estimate guess. Instead, we want an interval guess. We want a range of values. Instead of saying, I think sigma is this one number, we want a range of values. So we're going to say something like, I think sigma is between some numbers. So I might say between 1.2 and 2.5. Okay. So this is the kind of answer we want, a range of values instead of one value. And then if it turned out that someone later on actually collected all this population data and calculated sigma, let's say they calculated sigma and they found out that sigma is 2.1. Then when you guessed that it was 1.7, you were wrong. But when you guessed that it's between 1.2 and 2.5, you were right, because 2.1 is between 1.2 and 2.5. So we're going to be trying to guess sigma today. Our best one number guess is S. But then we're going to take the S and we're going to build an interval around it. So we're not just going to have a one number guess. We're going to have a range of values guess. And the reason for that is because we want to have a high chance of having the right answer. Okay, so that's the story. That's the same story I keep telling you, just it's about standard deviations today. Now, it's possible in this section they can ask you to estimate a variance instead of a standard deviation. We're not going to do any problems like that in here. And you're not going to see lots of problems like that in online homework. And I won't even be putting that on an exam or the final or anything. But if they did, then they're asking you to find sigma squared instead of sigma. Sigma squared is variance. And your best guess for that would be S squared. So sigma squared is basically the square of this number, but it's the variance of these numbers. If they're asking for that, you find the variance of these numbers, that's S squared. And S squared is your best one number guess for sigma squared. Now, I'm not going to go over that because let's say you build an interval and you get sigmas between 2 and 5. So I'm going to teach you how to build confidence intervals for standard deviation. The standard deviation sigma will be in the middle, and you'll get an interval something like that. Sigma is between 2 and 5. If they ask you to build an interval for the variance, all you have to do now is do what I've already taught you, and then just square everything. So you just square this, and square this, and your interval for the variance would be, the variance is between 4 and 25. So if they ever ask you for the variance, just do what I'm going to teach you today. Build the confidence interval for standard deviation, and then one extra step, square everything. But again, we're not going to spend time doing that one extra step because I'm not going to ask that question. Let's see what else it says over here. So our goal is to estimate the standard deviation of all the numbers in this big bag of data that's called sigma, or the variance sigma squared, depending on what the question asks. Because again, this is an imaginary bag of data. It's a huge bag of numbers that we didn't collect. Okay, so, and sigma is the standard deviation of all those numbers, so we're going to be guessing at it. Okay, And again, the way you guess it is you take a sample, calculate the corresponding thing for the sample. So if you're trying to guess sigma, which is standard deviation of these numbers, you calculate the standard deviation of the sample numbers, which is S, and that's your best guess for sigma. If the question asks you to estimate the variance of these numbers, you calculate the variance of these numbers, S squared, and S squared is your best guess for sigma squared. That's what it says here. S is your best point estimate for sigma. It's your best one number guess for sigma. S squared is your best point estimate or one number guess for sigma squared. And then we're going to build an interval around it. We don't just want a one number guess. We're going to build an interval around it. Okay, what does it say here? Why do we care about population standard deviation? Okay, standard deviation and variances tell us about consistency. Consistency is something very important in a lot of different places. I will give you one example. I can give you a ton of examples. Let me give you one example, and maybe I'll give you a second one. Let's see. But like, for example, the market, okay? So when you go to the market, you buy, fruit or whatever, chocolate or whatever you buy, they get shipments from companies, right? Like, okay, some company is going to deliver the strawberries, for example. Some other company is going to deliver the bags with Snickers in it or whatever it is. Okay, let's talk about Snickers. The little tiny Snickers, right? They have weights on them. A machine is making these Snicker bars, okay? And it's labeled, it says, okay, each bar is 20 grams or whatever it is. But when a machine makes a Snicker bar, it's set to make the Snicker bar weigh 20 grams, but every Snicker bar doesn't weigh exactly 20 grams. Some of them weigh more, some of them weigh less. So let's say you're going to deliver a shipment of Snicker bars to a market or whatever. So when the big truck with all the Snicker bars comes in, let's say, we have to measure consistency. Do they all at least weigh really close to 20 grams? Or are their weights really far apart, really spread out? That's why I want to know standard deviation. Standard deviation measures how spread out things are. And if the standard deviation is small, it means the weights are not that spread out, which is what you want. You don't want one candy bar. You don't want all the candy bars to say 20 grams on them, but one of them is like 5 grams, one of them is like 30 grams. Then the person who buys it, if it's 5 grams, they're going to be annoyed, kind of thing. So you want consistency. So that's what standard deviation measures. It'll measure consistency. Like, want the weights to be consistent, for example. Let's say this truck is delivering 1 million Snicker bars to the market. You're not going to calculate the standard deviation of the weights of all of them. That would take you forever. So what you do is you take a sample, and this is a very common thing that happens in markets, okay, is you'll take some of them out. Maybe you'll take 50 Snicker bars, measure the standard deviation of those, and then you'll look at that answer and you'll build an interval, and then if the standard deviation for all of the Snicker bar weights is something acceptable, you'll accept the shipment of Snicker bars. Otherwise, you'll say, no, 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 the weights are very inconsistent, and you reject the shipment. This is one example of why standard deviation is very important. So markets, for example, will use that. Another quick example is, like, let's talk about like sports, like basketball, for example. If you are going to get a player, let's say you own a basketball team and you want to, hire this player. Do you want the player to be consistent or not consistent? You probably want them to be consistent. You get a good player, maybe you want them to score 40 points a game, kind of thing. Okay. But if the player one day only can score 4 points and they're missing all their other shots, and the other day they score, 50 points, the player's very inconsistent. You're not going to want that. So you're going to want consistency. Now, you can decide whether or not to play the player or not. That's a different story. But you would want, if possible, every game this player gives you 40 points, kind of thing, or very close to 40 points. So again, standard deviation measures how spread out things are, and it will tell you about consistency. So is the player consistent? Can they put up 40 points a game? Or is it like, someday they have really bad days, some days they have really good days? You want to get an idea of how consistent the player is, kind of thing. One other thing to tell you is the difference between standard deviation and consistency. They're actually opposites. This is going to be more important when we get to chapter 10 after the exam. But standard deviation and consistency are opposites, meaning a high standard deviation is going to give you a low consistency. Because if the standard deviation is high, what that means is the numbers are very spread out. What does consistency mean? It means the numbers are all close together. Okay, so big standard deviation numbers are way spread out, so you have a very low consistency. Okay, and if you have a low standard deviation, that means the numbers are all close together. That means you have a high level of consistency. So just so we know, standard deviation and consistency are almost the same thing, but they're actually opposites. When one is big, the other is small. When one is small, the other one's big. Okay, so standard deviation is a very common, building confidence intervals involving standard deviation is a very common application of stats, especially when you're trying to decide if you should accept the shipment or reject the shipment from whatever company. Okay, and then this last little part here says, make sure to read the problems carefully. Okay, this is a more important comment in chapter 10, but it's important in chapter 9 as well, and chapter 8. So as far as your exam goes, read the problems carefully, because the number one biggest mistake that I see from students is I'll give them a certain type of problem, and the student will think it's a different type of problem. And like if I'm asking you to build a confidence interval for sigma, okay, and you build a confidence interval for mu, you're pretty much going to not get any points on that problem. It's possible there's a tiny bit of partial credit you can get. It's possible. But most of the time, if you think it's one kind of problem and it's another kind of problem, you're going to get a 0 on the problem, because you're going to use the wrong formulas, the wrong table, everything that I look for is going to be wrong. So make sure you read the problems really carefully on this exam and next exam and the final and all that stuff. And first thing we need to practice is recognizing what kind of problem it is. Let me give you a quick example. For your exam after this one, exam 4, that's on hypothesis tests, there's going to be 5 problems on the exam, just 5 problems. I can't put more because the problems take a long time. You'll never finish if I put too many problems. And I can't put too few, because if the less problems I put, the more each one is going to be worth. So you're going to have 5 problems on exam 4. Each one's going to be worth 24 points. That's 2 letter grades. Okay, so when you're doing a problem, if just one problem you mess up on, like when I say mess up, I mean you think it's one kind of problem, but it's a different kind of problem, you're most likely going to get a 0 on that problem. Like I said, it's possible to get 1 or 2 points. I do give partial credit, don't get me wrong, but you'll have to know what kind of problem it is first, and then maybe mess up down the road, and then you'll get some partial credit. But if you think it's a totally different problem than what it is, then you're most likely going to get a 0, and that's going to hurt your grade a lot. So this is one thing you want to practice from here forward. And we're going to do a little bit of that today at the end, towards the end of class, if we have time. It's just practicing, read the problem. Can you tell me what kind of problem it is? Okay, just watch out for that. I'm just giving you advice. If I ever scare you with something I'm saying, use it as motivation, okay? Like, oh, okay, I'm going to be on the lookout for that, and I'm going to study that a little bit extra. Don't be like scared and give up. You know what I'm saying? I want you to be, so it's okay to be a little scared as long as it pushes you to work harder. Okay. But if you're so scared that you're going to quit kind of thing, then don't get that scared. Okay. All right. Let's keep going. So again, I'm just going to say the story that I've told you a couple times. I'll say it one more time. So in section 9.3, every stats problem is about a big group. If you collect data from an entire big group, you get a big bag of numbers called the population data. We don't have the population data. So population data is an imaginary bag of numbers. It's a big bag of numbers. And what we're trying to figure out in section 9.3 is the standard deviation of all the numbers in this big bag. We don't even have this bag. So what are we going to do? We're going to guess sigma. Our best point estimate for sigma is S. So we're trying to guess sigma today. Our best one number guess is S. That means take a sample, look at a small group of numbers, and this number is your best guess for sigma. If it's a variance problem, then we're guessing S, sigma squared, and our best guess for sigma squared is S squared. But we don't like point estimates because they're almost always wrong. Okay, so what do we want instead of a point estimate? We want an interval estimate. So we want an interval estimate. We want a range of values so that we have a higher chance of having the correct answer. So instead of saying, I think sigma is 1.7, just the one number 1.7, and you're done talking, instead we're going to say, I think sigma is between these two numbers. That way we have a higher chance of being right. Okay, but we don't want the interval to be too wide either. And I keep telling you this, because if it's too wide, then we won't have useful information about the population that we're studying. For example, the Snicker bar, candy bar weights problem. Let's say you get sigma is between 0.1 grams and 0.2 grams. Maybe that's acceptable. You're saying sigma is a very small number. It's between 0.1 and 0.2. Then you'd be like, okay, cool, accept the shipment because sigma is a very small number. If you get something like sigma is between 7 grams and 15 grams, you might go, oh, sigma's big, reject the shipment. We're not taking those Snicker bars because sigma is a big number, so it's very inconsistent. Whereas here, sigma is a small number, it's very consistent. But if you get something like sigma's between 0.1 and 1,000, when you look at this interval, you don't have an idea. Is it a small number or is it a big number? Okay, that's because it's a very wide interval. When I say wide, I mean these two numbers are very far apart. When they're very far apart, okay, we might be certain that sigma is between these numbers. Sigma might for sure be between 0.1 and 1,000, but I have no idea. Should I accept the shipment or should I reject it? It's not useful information. So we don't want the interval to be too wide. Remember, we're trying to guess sigma. We're going to be, if your interval is very wide like this, then you're 100% certain that sigma is between those two numbers. So that's the good news. But the bad news is, again, I don't know if I should reject the shipment or accept the shipment. So we're going to want to compromise. We don't want a one number guess. It's almost always wrong. We don't want too wide of an interval because even though it's for sure going to be right, it doesn't give us useful information. Like, should we reject the shipment or not? So we want to compromise. The compromise is called a confidence interval. And every confidence interval is going to have a probability attached to it, which is called the confidence level. And the confidence level is going to be the probability that that we end up with an interval with the right answer in it. And we're going to be okay with that probability not being 100%. That probability is going to be a very big number. Every time I ask you to build a confidence interval, you're going to build a 98% confidence interval or a 95% confidence interval. The probability is going to be a big number, but it's not going to be 100%. So whenever you build a confidence interval, you're not going to know for sure if sigma is between the two numbers that you produced. But if it's like a 98% confidence interval, there was a 98% probability that you'd end up with an interval with the right answer in it. So most likely sigma is between the two numbers that you got, but you're not certain. So it's a little bit unsettling because normally in a math class, you want to be certain your answer is right, that's it. In this class, okay, you did the problem right, you're going to get credit for the answer, you get full credit. But then if I say, is sigma really between those two numbers, you're not 100% certain, you don't know for sure. That's the way confidence intervals work. That's the way stats problems work. Everything has a probability attached to it. Okay, so every interval estimate has a probability attached to it called the confidence level, and the interval is called the confidence interval. And again, the confidence level, that probability, is the probability that you'll end up with an interval with the right answer in it. So we want that confidence level to be high. We want a high probability of ending up with an interval with the right answer in it, but we're going to be okay with that probability not being 100%. Because again, it'd be too wide. So think of a point estimate as like a 0% confidence interval. We have basically a 0% probability of having the right answer. A too wide interval is like a 100% confidence interval. For sure we have the right answer in our interval, but our interval is not useful to us anymore. And then we're going to have a compromise. And our compromise is called the confidence interval. It's going to have a confidence level, which is it's going to have a very high probability attached to it, but not 100%. And once again, this last little thing, I need to rewrite this. All right. So, I've been talking a lot, telling you the story. I'm going to give you some formulas, and then we'll go ahead and do a problem. And also, just to remind you, in this section, you can use a different table called the chi-square table. So in section 9.1, like I said, if you're building confidence intervals for P, you're going to use the Z table. So every time you're building a confidence interval for P, use the Z table. In section 9.2, you're building confidence intervals for an average. Every time you're building a confidence interval for an average, you're going to use the T table. For the problems that we're going to do today, we're building confidence interval for sigma or sigma squared, but like I said, we're not going to do any of those. you're going to use a different table called the chi-square table. That's chi right there. That's a Greek letter. Chi-square table. Okay. It looks like it says chi, but it's chi. So it's a new table. It's a new random variable. And it says here in this slide, nothing is being squared. It looks like something is being squared, but nothing is being squared there. That's just the notation for the variable. It's called chi-squared. It's not like we have chi and we're squaring it. Okay, the random variable in this section is called chi-squared. When do you use the chi-square table? When you're building confidence intervals for sigma. Okay, and some of it is similar to the t-table. Some of it is a little bit different. Every table is a little bit different. But there's many different chi-square distributions, one for each sample size or one for each degree of freedom. Every row of the chi-square table is a different chi-square distribution. So you got to figure out what row to use by figuring out the degrees of freedom. So degrees of freedom will tell you what row to use. And then here it says chi-square distributions are not symmetric. They start at 0 and have a tail going to the right forever. So the picture for a chi-square looks like this. Okay, so it doesn't look exactly like the z and the t distribution. It starts at 0. So if you go this way, there's no curve. It doesn't go like this. There's no curve over the negative numbers. Okay, so the curve starts at 0, it goes up, and then it takes its time coming back down, and it goes to the right forever. The curve goes to the right forever, but it starts at 0. Okay, so there's a bump, but then it just bends the other way and it goes like this, gets closer and closer to the x-axis forever, and it goes to the right forever. Okay, so just remember that chi-square distributions all look like that. And the possible values for chi-square are 0 to infinity. Remember, every random variable you can think of as a bag of numbers. And for z distribution and t distribution, the bag has all real numbers in it. But chi-square doesn't have any negatives in it. The numbers that can be drawn out of the bag are the numbers where there's a curve above it, and the numbers where there's a curve above it are the numbers from 0 to infinity. So only positive numbers. That's part of the reason why they call it chi-squared, because one thing you know about squaring something is that when you square something, you never get a negative. Okay, so that's part of the reason they're calling it chi-square. All the values are positive on the axis down there. Okay, when you're building a confidence interval for sigma, so that's what I have to teach you, right? How do you build a confidence interval for sigma? When you build confidence intervals for P, you had to find Z alpha over 2. When you're building confidence interval for mu, you had to find something called T alpha over 2. When you're building confidence interval for sigma, there's 2 numbers you got to look up in the table, not just one. I call them chi-square left and chi-square right. That's not the notation your book uses. Your book uses a different notation. I don't like the notation your book uses, just too ugly. But be prepared in online homework for them to use a different notation. And if it confuses you at all, I mean, I can go over it, but otherwise, learn what I'm going to teach you how to find, and you're going to be looking up 2 numbers. And then when they ask you to type those numbers in, and they use a different notation, just take one of your numbers and type it in, and if it says it's wrong, then put your other number and type it in, kind of thing. But I think the book's notation, if we care, I think this one is called chi-squared 1 minus alpha over 2, and this one's called chi-square alpha over 2. But it just gets a little too ugly. So I call it chi-square left and chi-square right. So you're going to have to look up 2 numbers in the chi-square table. To find these numbers, what you're going to do is you're going to have to find the degrees of freedom so you know what row of the table to use. You'll draw a picture. The picture is going to look like this. In the picture, chi-square left is on the left, chi-square right is on the right. Makes sense, okay? Chi-square left on the left, chi-square right on the right. You're going to go up to the curve and you're going to shade the ends. Don't shade the middle there. That middle area is the confidence interval, but you're not going to be shading that. You're just going to be shading the ends. And each one has area alpha over 2. And then you can look up these 2 numbers in the table. Let's see what it says here. So again, degrees of freedom are on the left of the table, just like the T table. And if your degrees of freedom is not there, pick the closest one. Areas to the right are on top. If it's not there, use the closest one. And then chi-square right and chi-square left are in the middle of the table, just like T alpha over 2. The T alpha over 2s were in the middle, chi-square left and chi-square right are in the middle. You'll see when we do an example. All right, let's move on. And here's a picture of the chi-square table, but again, download it from my website. Again, notice the degrees of freedom are here. Okay, and here it says area to the right. Every table is different. Z table, you need to know area to the left. T table, you need to know area in the right tail. Has to be in the right tail. This one doesn't say area in the right tail, it just says area to the right. So it's like the opposite of Z table. Z table is area you need area to the left. This one you need area to the right. Once you know the area to the right of the number you're looking for, then the answer is going to be in the middle. Your chi-square left and chi-square rights are going to be in the middle here. Okay, again, I'll show you how to do it when we do an example. All right, let me give you some formulas and then we'll do a problem. Today, the letter we're trying to guess is sigma or sigma squared, again, depending on if they want standard deviation or variance. Our best one number guess for sigma is S. Our best one number guess for sigma squared is S squared. Alpha formula is 1 minus the confidence level, like it always is. Degrees of freedom formula is n minus 1, like it is going to be for a while. Okay, so the formula for degrees of freedom is going to be n minus 1 for a while. And then here is the formula for the confidence interval. So one thing to understand, there's no margin of error in this section. No margin of error. Okay, let me back up again. If you were building a confidence interval for P in section 9.1, what you would do is you take your P hat answer and add and subtract the margin of error. If you were building a confidence interval for mu, what you would do is you would take your X bar answer and add and subtract the margin of error. Now we're building a confidence interval for sigma. You might think take S and add and subtract the margin of error, but this is not what you do in this section. So some things are a little different. There's no margin of error in this section, because if there was a margin of error, then whatever your S answer is, you would go to the left, the margin of error, and the right, the margin of error. And your interval would be between here and here, and S would be right in the middle of your interval. And that doesn't happen for standard deviation problems. It turns out that whatever your interval guess is, S is not right in the middle. It's actually usually on just on one side. It's kind of lopsided, like S would kind of be like right here, but then your interval would be like this. It's not in the middle. So no margin of error, but that actually makes it easier. Basically, I'm just giving you the formula for the confidence interval. There it is. Okay, notice I have sigma in the middle because that's what we're guessing. We're guessing sigma is between these two numbers. You just calculate these two numbers, and sigma is between those two numbers. If you're trying to find the confidence interval for the variance, you would just square everything. Again, we're not going to really do it, but if you square this and square this and square this, when you square a root, the root goes away. So this root and this square go away. This root and this square go away. This will stay here. And if you wanted a formula for the confidence interval for variance, we get that. Again, the formula just looks like looks just like the top one, but the roots are gone. And instead of sigma, it says sigma squared. But I'm really not going to be using the bottom whenever this is the formula we're going to use. All right, let's go on to what else? Condition. Okay. Once again, let me remind you, essential limit theorem applies to everything we're going to do for the rest of the semester. So that means we're going to be assuming that the original bag of data, the population data, that imaginary huge bag of data that we don't have, we're going to assume those numbers have a normal distribution. So the essential limit theorem applies, and so all the formulas that I give you, they're derived assuming essential limit theorem. You don't need to check that or anything, but if it shows up in the online homework, if they're talking about it, I want you to understand that, you know, there's always some condition we need to make sure essential limit theorem is applying. So there it says population from which samples are drawn, which means population data bag has a normal distribution. Okay, and then I already mentioned this, but let me read it again. It says confidence intervals for sigma are not constructed by finding a margin of error and adding and subtracting it from S. There's no margin of error. Okay, so you don't take S and add and subtract the margin of error. Instead, you just use the formula. Okay, so it's even a little bit easier. And as I mentioned before, confidence intervals for sigma are not symmetric about the sample statistic. In other words, if you're guessing that sigma is between here and here, S will not be in the middle. S will be kind of off to one side. That's why it says it's not symmetric, meaning it's not like S is in the middle. S is off to one side. That's what that says. And I've already told you that. And that's the end of the story. So I've told you the story. The story has been completely told. Now we just have to be able to do some examples. Before I do them, any questions? All right, sounds good. So let's go to example 1. Okay. A jar of peanuts is supposed to have 16 ounces of peanuts. The filling machine inevitably experiences fluctuations in filling, so a quality control manager randomly selects 12 jars of peanuts from the storage facility and measured their contents in order to estimate the standard deviation of the number of ounces of peanuts in all jars filled by this machine. She obtains the following data. Okay. Before we continue reading this problem, let me explain some things. So look, when you get a jar of peanuts, it's filled by a machine, right? So the jar goes and peanuts get filled in there and then it gets sealed, whatever. And if it says 16 ounces of peanuts, that means the machine is set to put 16 ounces of peanuts in each jar. But each jar is not going to get exactly 16 ounces of peanuts. You can look at the data here. Oops. If you look at the data, you can see none of them say exactly 16 ounces. Some of them are less, some of them are more. And it makes sense. Some jars get maybe a couple of extra peanuts, some jars, maybe a couple of peanuts fall out or whatever. It's just so hard to get it exactly 16 ounces. Okay. But we set the machine to make it 16 ounces. So now what we want to do is want to measure, is the machine consistent enough? Okay, if they're not all exactly 16, are they all close enough to 16 where we're happy? Or are they too far apart? Like if one jar says 16 ounces of peanuts and there's only 10 ounces, the customer will be mad. So they paid for 16 ounces, they got 10 ounces, and you'd be mad too. That's a very inconsistent machine. So I want to know basically, are the weights of the jars or the amount of the weights of the peanuts in the jars consistent? Is the machine doing a good job making them all very close to 16? Or is it so spread out that we need to fix this machine or something? So to figure that out, we want to know, it says here, in order to estimate the standard deviation of the number of ounces of peanuts in all jars filled by this machine. This machine may have filled millions of jars. If you took the weights of all million jars and found the standard deviation, that's what I want to know, the standard deviation of those weights. So I can get an idea of the consistency level of this machine. But I don't have all million jars. Some of them have been sold and eaten, you know, kind of thing. So I don't even have the data. So what are we going to do? We're going to take a sample. It says the quality control manager samples 12 jars that were made by this machine and measured the weights of those 12 jars. So we got the weights of 12 jars. We're going to find the standard deviation of these weights, and we're going to use it to estimate the standard deviation of the weights of all jars made by this machine. Okay, so we're going to look at the standard deviation of 12 numbers to estimate the standard deviation of 1,000,000 numbers. That's what's happening. Because I don't have the 1,000,000 numbers, we're going to guess it by using the standard deviation of these 12 weights over here. All right, let's go on to the next one. So it just asks you these questions. So part A through E, again, that's first day of class stuff, sort of. Okay, what's the population sample, all that stuff. And then after that, we will answer these questions where we're building a confidence interval. Okay, let's start with the population. Who can tell me what the population is?
All jars of peanuts.
That's almost right. Let me write down what you've said. All jars of peanuts. You would need to probably say a little bit more than that, though. All
Filled by the machine?
Filled, yeah. Filled by this machine. So in this problem, there's one machine. That's what we're checking. We're analyzing this one machine to see if it's consistent or not. So there's just one machine. And the population is all the jars that have ever been filled by this machine. So in this problem, there's one person, there's one machine. Population is never one person or one machine. It's a big group, okay? It is a mistake that I see sometimes. People will say the population is the one employee at McDonald's or something like that. And that doesn't make any sense. Population is a big group. So it's not the one employee. So same thing here. It's not the one machine or it's not the one quality control manager. We are focusing on one machine, but the population is all jars filled by this machine. Also notice the population is not always people. Today it's jars of peanuts, okay, instead of people. Okay, part B, what is a sample? Someone tell me what the sample is.
12 jars of peanuts.
Yeah, it's those 12 jars that we have, right? So let's see. The 12 jars of peanuts filled by this machine that the quality control manager selected. One thing that I mentioned first day of class, but let me mention it again. When you're trying to be clear, so you want to be clear, right? This is communication. You're going to write these things out in words. You want to be clear. And one way to be clear about things is if you're not sure, throw in some extra words. Give me a little more detail so it's a little more clear. Sometimes it's okay if you don't do that, but in general, put in some more words and make it more clear. But when I say put in some more words, sometimes if you put in some, you might put in some wrong words and all of a sudden it's wrong, okay? But, you know, someone might just write the 12 jars. I would probably accept it. But look at what I'm writing here. I'm making it really clear which 12 jars we're talking about. Okay, so that's the idea. So this is part of your, you know, in college in general, one thing you want to always work on is communication. So the way to communicate, to try to communicate a little more clearly is just put in some extra words. All right, there's the population, there's a sample. Now population parameter. Okay, today the population parameter is sigma, but how do I know that from the problem? It says we're trying to estimate the standard deviation, okay? Sometimes the word is not there. They might not say the word standard deviation, but if they use the word consistency, for example, that's another one that lets you know that the population parameter is sigma. All right, so now we got to describe it in words. Whenever you describe sigma in words, the very first thing you have to write down is the standard deviation. So pay attention to this, because even though we went over some of this first day of class, we didn't know what standard deviation was first day of class. We didn't know that till second day. So we didn't work on describing it in words before. Okay, so this is a little bit new. So when you're describing it in words, first thing you write is the standard deviation. And then after you write that, standard deviations can only be calculated from a group of numbers. So the next thing you have to mention is what are the group of numbers they're finding the standard deviation of. Sometimes someone will say standard deviation of the jars of peanuts. Jars of peanuts are not numbers. They are jars of peanuts. What about the jars? And it's got to be a number. What about the jars are we finding the standard deviation of? Someone tell me.
The ounces.
The number of ounces.
Yeah, you can write the number. I'm going to write the weights, but if you write the number of ounces, that's totally fine. I think it says that number of ounces in the problem somewhere. Yeah, number of ounces. But again, I'm just going to write the weights. Standard deviation of the weights. Because again, number of ounces or weights, that's a number. Standard deviation of the weights of, and now you're going to mention the population of all jars filled by this machine. Once again, what I'm saying is, if you just happen to have every single jar filled by this machine, all millions of jars, if you got the weights of all of them, so you have a million numbers, and you found the standard deviation of those million numbers, that's what sigma is. But again, in reality, we don't even have the jars, so we can't even collect the data because we've sold those jars or whatever. So we're going to guess sigma. How do you guess sigma? You take a sample and you calculate the standard deviation of the numbers in the sample, which is called S. Part D, what is your sample statistic? The symbol is S. When you describe it in words, you're basically going to say the same thing, but when we mention the population, which was this part, you're going to change it to the sample. So it's the standard deviation of the weights of the 12 jars that are in the sample, of the 12 jars filled by this machine selected by the quality control manager. I'm just writing down what I wrote earlier for the sample. So instead of the thing that's boxed there, we changed it to this. Okay, because that part is the population. Now I just changed it to the sample, but everything else stays the same. Okay, so those are the symbols. That's how you write it in words. And then we got to find the value. But before I do that, any questions so far? Okay. So I'm not asking you to find the value for sigma because it's an unknown number, but we can calculate S because we have the data for it. So I'm going to go back to our data. We're going to go ahead and calculate it. All right. So I want to know the standard deviation of these numbers over here. So the way you do it, we did it last class. Let's go ahead and do it again. First thing you're going to do is you're going to find two sums. So again, I just want the standard deviation of these things. So one sum of x squared. So you got to square each number, then add them. That's one sum you always have to find when you're looking for standard deviation. 15.94 squared plus 15.74 squared. Okay, so this is me taking you back to second day of class. How do you find standard deviations? Oops. So you square each number and then add them up. That's the first sum you got to find. All right, give me a second to do that. You guys should be doing that on your calculator as well to double check my answer, but give me a minute here. Okay, the answer I'm getting for this is 3032.1999. Okay, so if you got that, you're in good shape. If not, do it over and over and make sure you're able to get it. If you don't understand how to do it, ask me. But again, I'm just saying square this, then square this, then square this, square each one of them, all of them, and then add them up. That's what sum of x squared means. Okay, any questions on that much? Okay, then you're going to find another sum, which is sum of x. Sum of x means, remember, x stands for your data. So it's x, these are the x's. And it just says add all your x's. Just add the data. So you don't square them this time. You just add the numbers. 15.94 plus 15.74. And this dot to dot means just keep going for every number in your data set up until the last one. And when you're done with that, the answer is 190.71. So when you're trying to find a standard deviation of some data, you first find these two sums. Then you plug it into the standard deviation formula. Standard deviation formula, I'll write it down here. It's sum of x squared minus fraction line, parentheses, square outside the parentheses. Inside the parentheses, it says sum of x. Then underneath it says n. And then we have over n minus 1 and square root of this. That's the formula. I'm going to give it to you, of course, on a quiz or an exam, but you still have to know how to use it. So there's the formula. Here it says sum of x squared. In place of sum of x squared, I'm going to put my sum of x squared answer there. So it's going to be 3032.1999 minus fraction line, parentheses, square outside. Inside the parentheses says sum of x. So inside the parentheses, I'm going to put my sum of x answer. I'm going to put the 190.71 in there. Okay, and then you divide by n. N is your sample size. It's how many numbers are in your data. There's 12 numbers. You can count them. There's 12, so put a 12 there. On the bottom, you're going to put 12 again, but minus 1. And then you're going to square root all this. And then you type that in the calculator. So it's 3032.1999 minus open parentheses 190.71 close parentheses square divided by 12. So the answer to I'm not going to write it down, but let me just say it real quick so that when you're redoing the problem later, you can check it with your calculator. The answer to just this much here on my calculator is like 1.34 or something. Okay. Then you're going to divide by this. And again, don't type 12 minus 1. Just type 11. So divide by 11. Now the answer on my calculator is 0.1219 something or other. And then you take the square root at the end. The way you do that, you do second square root, second answer. And the number I have for the final answer, I'm going to write 0.349. And this has units, ounces. Okay. So whatever the units are for these are all in ounces. The standardization will also be in ounces. Okay, that's that one. Again, why did I go to 3 numbers after the decimal? Again, you can go more. If you're not sure, always put a couple extra digits. Okay, questions? All right, 0.349, let's go. You know what, let's just go ahead and go to 4. Most of the time we go to 4 numbers anyway. So 0.3492. That goes here, okay. Okay, so the standard deviation of the weights of those 12 jars of peanuts is 0.3492. But I want to know the standard deviation of the weights of all jars made by this machine, which is sigma. I don't know it. I don't have the data for it. What's my best guess? The 0.3492. That's my best guess. It's probably a bad guess, but it's my best guess. And that's what we're going to write over here. Sigma is approximately S, which is 0.3492 ounces. All right, that's part E. Any questions up to part E?
No.
Okay, so that's pretty much first day of class stuff. I mean, there were some things that we hadn't seen, but now the new stuff is coming. Okay, so now building confidence intervals. All right, part F, find a 90% confidence interval for the population parameter. So now instead of giving me a 1 number guess that sigma is 0.3492 ounces, give me an interval guess. Give me a range of values. So the way you're going to do that, you're going to do that in 3 steps. Most of the time, actually I take it back. You're going to do it in 2 steps. First thing you're going to do is you're going to find chi-square left and chi-square right. Sorry, some of my chi-squares are sloppy. Chi kind of looks like an X, okay? Except on this side there's like a little curl, and on this side there's a little curl. So what I do is I do that, and then I finish an X. That's what chi looks like, okay? And then squared. So sorry, some of them are a little sloppy here. Let me draw it a little bit better. Chi squared left, what is that? And then chi square right, what is that? Now, some of it's going to be, again, similar to the way we did things in the last couple of sections. So you're going to start off by writing alpha is 1 minus the confidence level. Similar to what we've done before. The confidence level is the 90%, right, as a decimal, 0.90. Minus 0.90 is 0.10. Then you got to divide it by 2. Always divide it by 2. So 0.10 divided by 2 gives you 0.05. Okay, then you're going to write down the degrees of freedom. N minus 1. Today n is 12. There's 12 numbers in our data, so degrees of freedom is 11. And then you draw a picture. So here's how the picture looks. You draw a number line. At the beginning of the number line, go up to the curve, go up, not to the curve, but just go up and then start coming back down, make like a little peak. But then you start bending the other way and get closer and closer to the x-axis without touching it, something like that. Label it chi-square distribution. Then you're going to put 2 tick marks, one on the left side, call it chi-square left. Put another tick mark on the right side, call it chi-square right. And when I figure out these answers, I'll write them below. So we have to find 2 numbers as opposed to the other 2 sections where you just had to find 1 number. Now you go up to the curve for both of these and you shade the ends. So you shade to the left of chi-square left and shade to the right of chi-square right. Don't shade in between. Okay, shade the ends. Each of those red areas is this alpha over 2. This area here is 0.05. This area here is also 0.05. That's why you divide it by 2, because each of those areas are the same. The total of the red area is alpha, 0.10, but you divide by 2 to figure out what each one individually is. They're both 0.05. Okay, now when it comes to chi-square table, this number is going to be the easy one to look up, and then we'll have to do a little bit extra work to look up the one on the left. Why? Because for chi-square right, I know the area to its right. In order to look up something in the chi-square table, you need to know the area to its right. Okay, so the area to the right of this one is 0.05, and degrees of freedom is 11. Let's go to the table. And again, the table reminds you, area to the right is what you need. Area to the right is 0.05, degrees of freedom is 11, and you go like this, and you go like this, and that number is 19.675. That is this number here. Any questions on the 19.675 number? All right, now, how do you find chi-square left? I need to know the area to its right. I know the area to the left of it. I know the area to its left, but I need to know the area to the right. When I say area to the right, I mean from this line to the right forever. I don't want to shade it because my picture is going to get too ugly. Maybe I'll do a bad job shading it so I can erase it after. But I mean from this line to the right of it. I shouldn't be going beyond the curve, but I'm doing that so I can erase it easier. And you go to the right forever, so including this area down here, okay? So not just the area that's in white, I want the area to the right of this line forever. Okay, let me erase it now. What I normally do when I draw these things on a quiz or whatever is I'll just put the arrow like you see there, pointing to the right. And that area, how do you find this area to the right? Well, it's just gonna be 1 minus this area. So this is gonna be 1 minus 0.05, which is 0.95. 0.95 is not just the white area. It's the white area and this area total, 0.95. If this is 0.05, the rest of it is 0.95, 1 minus that. Okay, so you have to do one extra little step when you're trying to find chi-square left. Because for chi-square left, you know the area to the left of it, I need to know the area to the right. Because that's the way chi-square table is. You need to know the area to the right in order to look up something. So the area to the right is 0.95, so you can look for 0.95 and degrees of freedom 11 on the table. Let's go back to the table. Again, it says area to the right. Our area to the right is 0.95 and our degrees of freedom is 11. So go like this and like this. And you get 4.575 for that one. And that's this number here. Any questions on looking up chi-square left and chi-square right? Okay, so you find those numbers. Now I will have to erase some of that. Here, let me take a picture of this real quick, because I need more room. So, okay. So we just found out chi-square left is 4.575. Chi-square right is 19.675. Make sure when you do this, you do everything that I just erased. So I'm going to be looking for all that, but I need to erase it because I need the room to finish the problem. So you find that, so you do that first. Then the next step, you could just find your interval now because we have a formula for it. So the interval. Okay, so the formula for the interval is n minus 1 s squared over chi-square left. Sorry, that's wrong. Chi-square right. And then sigma in the middle. And then n minus 1 s squared over chi-square left. So I'm going to be giving you the formula, so don't worry. But let me just mention this in case you do worry. I want you to notice in the formula, chi-square right is on the left and chi-square left is on the right. So when I give you the formula, you might go, did he do a typo? Is it a typo? So this is the way it works. In the picture, when you draw the picture, chi-square left is on the left, chi-square right is on the right. But in the formula, they're backwards. Okay, chi-square left is on the right, chi-square right is on the left. But again, just trust me that I didn't make a typo when I give you the formula. Then you'll be okay. Now I'm going to go ahead and plug in everything. Remember, n was 12, so we have 12 minus 1 in the parentheses. S squared, remember S was 0.3492 squared. We'll go back a couple slides here. Okay, so here's S, 0.3492. Okay, so you put that in there. Chi-square right is 19.675. Okay, I'll put the square root sign in a minute, but let me mention one more thing here. Again, if you look at this, you might think you should square something. Don't square anything on the bottom. Chi-square right is 19.675. You don't square the 19.675. The bottom number is just whatever answer you got for chi-square right. But on top, when you see s squared, there we are squaring something. Okay, you got to square your s. And then square to this. All right, sigma here. And then on the right side, n again is 12. S again is 0.3492. We are going to square that. On the bottom it says chi-square left. Don't square anything. Chi-square left is 4.575. And you square root that. And now you just calculate those two numbers, and then you're good. So here's what I'm doing. 11 times 0.3492 squared divided by 19.675. Answer. And I'm taking the square root, second answer. And on this side, I'm getting 0.2611 ounces. Remember, the weights are in ounces, so sigma is going to be in ounces as well. The other side, 11 times 0.3492 squared divided by 4.575, get the answer, and then take the square root, second answer. And I'm getting 0.5415. And that's how you build a confidence interval for sigma. So I told you a very long story, but really, it's really not that much. It's you look up chi-square left and chi-square right, and then plug into the formula, and you have your interval. Story's over. Story's not completely over, but story for part F is over. Any questions on part F? Okay. Now, remember we're trying to figure out sigma, which is standard deviation of the weights of all jars of peanuts made by this machine. Our best one number guess was 0.3492, was S. That's our best one number guess. But now we're saying, okay, a better guess is we think standard deviation is somewhere between 0.26 and 0.54 ounces. Okay, so it's a better guess. It's instead of saying it's this one number, 0.3492, and that's it, we're saying it's, well, we think it's somewhere between here and here. And then, so that's a better answer because we have a much higher chance of being right. Because again, if it turned out that someone figured out what sigma is and it was 0.4, well, when you said it was 0.3492, you were wrong. But when you say it's between these two numbers, 0.4 is between those two numbers, so now you're right. Okay, so last chance, any questions? This is the most important part of example 1, part F. Any questions on part F? Okay, we're gonna do part G in a minute. Let me move on to part H. One thing that I like about this section, and just in general, I taught you how to build confidence intervals, okay? But after you build the confidence interval, you would like to answer a question. You don't want to just say, here's my confidence interval. Oh, it's pretty. You look at it and you're done. Now I want to take the confidence interval and answer a question from it. So I'm going to go ahead and I'll come back to G, but part H is asking a question. The quality control manager wants the machine to have a population standard deviation below 0.20 ounces. Does the confidence interval validate this desire? Okay, so in our problem, let me go back. Sorry, I forgot what it was. I'm going to take a picture of these numbers. Okay, so if we go to part H. Okay, so our confidence interval was 0.2611 ounces. So sigma is between, or we're guessing anyway, that sigma is between 0.2611 ounces and 0.5415 ounces. That's our guess. Now they're asking us, it's kind of like, you work at this company and they're asking you, is our machine good enough or do we need to fix it or replace it or something? Okay. It says the quality control manager wants to have a population standard deviation, that's sigma, below 0.20 ounces. Remember, the smaller the standard deviation is, the smaller sigma is, the more consistent the machine is. The quality control manager wants the standard deviation to be less than 0.20 ounces. In other words, less than 0.20 ounces is acceptable. If it's not less than 0.20 ounces, we got to fix the machine or replace it and buy a new machine or something like that. Okay. Now it says, does the confidence interval validate this desire? We want sigma to be below 0.20, but we estimated that sigma is between these two numbers. Does the confidence interval validate this desire? Yes or no?
No.
No. No. Yeah. So look, you're saying you think sigma is between 0.26 whatever and 0.54 whatever. If you're right, there's no way it's less than 0.20 because every number from here to here is bigger than 0.20. Yeah, so it's not really much to write down. The answer is no. I'll let you write some words down for how to explain it, but maybe I'll draw a picture here. So there's 0.20. So there's a number line and there's 0.20. And this is what we want. We want sigma to be in this green section. We want it to be less than 0.20. But our interval says that it's between 0.2611 and 0.5415. So we're guessing that our sigma, but we think sigma is in this red region here. So we want it to be here, but we think it's here. So the confidence interval says, no, we're not here. Okay, so that's the idea. And again, you can write down more stuff. If you want to write something down in words, I guess I'll say it once, but I'm not going to give you an official thing to memorize or anything. Just make sure you guys get the general idea. If you believe the confidence interval, okay, then sigma is somewhere between 0.26 and 0.54, then it cannot be less than 0.20. So what the quality control manager wants can't happen if you believe the confidence interval. Does the confidence interval validate the desired? No. So what would you tell your employer? You'd say, okay, something's up here. We got to either fix the machine or get a new machine, that kind of thing. So you see, it's a useful result. We got a confidence interval, and from the confidence interval, we're able to answer a question that's useful to the company. Do we need to fix the machine or that kind of thing? All right, I'm done with part H. Any questions on part H? So also remember that when you build a confidence interval, it doesn't mean for sure that sigma is between here and here, but pretty much you believe the interval. They're asking, does the confidence interval validate this desire? So again, it's like, if you believe the confidence interval, do we have what we want? No. If you believe the confidence interval, then no, sigma is not less than 0.20. But there might be some people in here who are not telling me and they're not getting why. So let me just say it one more time. The confidence interval is telling you that sigma is between these numbers. I don't know what it is, but any number that's between those is over here. It cannot be less than 0.20. The fact that this is bigger than 0.20 and this is even bigger, that means sigma is definitely bigger than 0.20. And we want sigma to be less than 0.20, so that can happen if we believe the interval. Okay, let's go to part G. What does a 90% mean in a 90% confidence interval? So it's the same answer that I keep giving you in chapter 9, just you're going to change the letter. Remember that we built only one confidence interval, okay? So when you build a confidence interval, you don't know if your guess is right. You don't know if sigma is actually between the two numbers you came up with. But if you build many confidence intervals, then most of them will have sigma in them. In this case, 90% will have sigma in them and 10% will not have sigma in them. The way you write it goes like this, is if you take many samples, and use them to build many 90% confidence intervals. So this first part, the important thing when I'm grading is that you're talking about many confidence intervals. Okay, so you build many confidence intervals, not just one. Then what's going to happen about 90% of those intervals. Please don't write 90% of the time, about 90% of the intervals will contain the correct answer. Or sigma. That's the only thing that changes. The letter is sigma today. About 90% of the intervals will contain the correct answer for sigma, and about 10%, I'm getting the 10% by doing 100% minus 90%. About 10% of the intervals will not contain the correct answer for sigma. Okay, two other comments I need to make here. So one of them, on the exam, what letter are you going to put here? Well, if this question comes at the end of a percentage problem, you're going to put the letter P here and here. If this problem comes at the end of an average problem, you're going to put mu here and here. If it comes at the end of a standard deviation problem, you're going to put sigma here and here. And if I give you a problem where it's on its own, like it doesn't come at the end of any problem, it's just one question by itself, then I don't want you to put any letter here and here. I want you to write in words the population parameter, because you don't know what the population parameter is. So you're going to say about 90% of the intervals will contain the correct answer for the population parameter, whatever it is. And about 10% of the intervals will not contain the correct answer for the population parameter. Okay, so if it doesn't come at the end of a specific problem where you know which population parameter we're working on, then don't write any letters there, just write the phrase, the population parameter. Okay, that's the first comment. The other comment I want to make, I saw a student do this. Every semester I get some students do this, and one student did it, at least one, that I can remember. So I want to warn you against this. For the second part, someone would write something like, about 10% of the intervals will contain the wrong answer for P. They'll write about 10% will contain the wrong answer for sigma or P or whatever it is. Don't write will contain the wrong answer. Every interval contains wrong answers. Intervals have lots of answers, and only one number could be what sigma is or P or whatever. So I don't want you to write the wrong answer, okay? Every single interval will have wrong answers in there. The question is the right answer captured in there, okay? So about 90% will have the correct answer, and about 10% will not have the correct answer, okay? Make sure you write it like that. Don't write will have the wrong answer, because like I said, every interval will have the wrong answer. Now, if you want to fix it, you can make it work. You can say about 90% of the intervals will be correct intervals, meaning they have sigma in there, and about 10% will be incorrect intervals or be wrong intervals, meaning they do not have the right answer in there. But to be more clear, write it this way. 90% will have the correct answer, and about 10% will not have the correct answer. It's all about, does it have the correct answer? They all have wrong answers. Hopefully that makes sense. All right. So that's how you're going to write that. Any questions on how to write that? Okay, one last thing. I keep mentioning this because this is a very important visualization. We took one sample, in this case of 12 jars of peanuts, and we built an interval for sigma. But I want you to imagine we do this over and over again. We take another sample of 12 jars and we build another interval for sigma. We say sigma is between these two numbers. We put our answer on an index card. Then we take another sample of 12 jars and we'll get another interval. Every time you take a sample and go through what we went through in this problem, you'll get another interval. Imagine you keep doing this, another 12 jars, another interval, write on an index card, and fill this bag up with millions and billions of index cards. Each index card has a confidence interval in it, okay? And what do I know about the contents of this bag? I know that 90% of the intervals are going to contain sigma, and 10% will not contain sigma. So when you build a confidence interval, you're only building one. It's like you're selecting one out of a bag that has a whole bunch of intervals in it. Okay, so we're just selecting one interval out of the bag. If you were going to select one interval out of a bag like this, would you guess that your interval would have sigma in it, or would you guess your interval would not have sigma in it?
Would have sigma.
90%
you
would.
guess it would have sigma. Why? Because so many of the intervals in the bag have sigma in it, 90% of them. It's so hard to, it's so easy to get one that has sigma because so many have sigma. It's hard to get an interval that doesn't have sigma, but still 10% of the intervals in the bag don't have sigma in there. So when you select, so constructing a confidence interval is like selecting one interval out of a bag filled with intervals that has these contents. 90% have sigma and 10% do not. So whenever you build a confidence interval, when you're done, you pretty much believe your interval, meaning you believe that sigma is actually between the numbers you got, because you believe that you selected one of the good intervals, one of the ones that has sigma in it. But is it possible you selected one of the bad ones? Is it possible your interval doesn't have sigma in it? Sure. That just means you got unlucky. You selected one of the 10% that do not have sigma in it. Okay, so this visualization, I don't need you to draw this or anything on a quiz, but I want you to understand it because it's a real good way of thinking about what we're doing. When you build a confidence interval, you pretty much believe that sigma is between the numbers you got because it's so hard to draw out of this bag and not get an interval that has the right answer for sigma in there because so many of them do, but it's definitely possible to get an interval that doesn't have the right answer. So if someone later on tells you, just so you know, I found sigma and it's not between the numbers you gave, then you'll say, okay, well now I know that I selected one of the 10% that don't have sigma. And that's what happens when we have a compromise, when we're okay with not being certain that sigma is in our interval, then there's going to be a high probability we'll end up with an interval with the right answer. It's like the high probability we'll end up selecting an interval with the right answer in it, and a low probability of selecting an interval or ending up with an interval that doesn't have the right answer in it. Okay, now I'm completely done with example one. Any questions on example one? So let's go on to example two. Example two is just another example of building a confidence interval for a standard deviation. So I'm going to tell you a couple of minutes story, but this problem is very similar to the last problem. This problem is about investing money and CDs and things like this. So let me just give you a 2-minute introduction to what's happening here. Because it says, if you read the first sentence, it says, investors not only desire a high return on their money, but they would also like the rate of return to be stable from year to year. Okay. Years ago, I used to teach people how to basically get rich off of CDs. Okay. Of course, you can't do it anymore, but there was a time. Let me tell you what a CD is. A CD, when you put your money in the bank, why do you put your money in the bank? The main reason is because what you're doing when you put your money in the bank is you're loaning the bank the money, is what you're doing. And they take your money and they loan it to other people, like, for to buy a car, to buy a house, things like this. And then what happens is, like if you buy a car, you make payments and you pay interest. In other words, you pay more than what you were supposed to pay because you took a loan. So the bank gives out the loan. When the loan is paid back, it's paid back with extra money. That's called interest. And then they'll give some of that to you. It's like saying, thank you for letting us use your money. Here's a little bit of interest. Now, it's not usually a lot, but that's why you put your money in the bank. That's one reason. You might have another reason, like, it's safe in the bank if you feel that it's safe in the bank, kind of thing. But that's the main reason. You're giving the bank your money because you don't want it to sit around at home and just collect dust. You give it to the bank and it collects extra money for you. They pay you as a thank you for you loaning them your money. But it's very little money. Okay, the amount of money they give you is very small. There used to be this thing called a CD, certificate of deposit. Actually, it still exists, just not as exciting anymore. And they used to pay you 5%, 6%, 7% on these CDs. Basically, what that means is a CD is like putting your money in the bank. You're putting your money in the bank, but you're telling the bank, I'm not going to come for this money for a while. So you're locking it up. It's like, you take maybe, let's say you have $10,000 just, and you want to go put in a CD. You go to the bank, say, I want to open up a CD, $10,000. You give them the $10,000. It's like it's in a bank account, but you can't touch the money for a certain amount of time. And you decide what that amount of time is. It could be 3 months, it could be a year, it could be 10 years. You're not going to touch the money at all. And as a thank you, the bank will pay you more interest. In other words, they're going to loan your money out, but because you're telling them I'm not coming back for a while, they're willing to give you more interest. And I used to teach people how to retire and off all this stuff. But here was the idea. The idea is you save money every month. You put your money in the bank every month during your working years, okay? And you hope that when you retire, you have $2 million in the bank. And I don't want to get into too much of it, but I went into all the details on how you can make that happen, kind of thing. You have $2 million in the bank, and now you're retired. You're 65 or whatever. You're retired. You have $2 million in the bank. Here's what a lot of people who have a lot of money do. They do things like this. There's $2 million in the bank. You don't spend that $2 million. If you spend it, once it's gone, you're gonna have to go back to work. You have no money. What are you gonna do? So you don't do that. What you do is the $2 million is in a CD. The CD will pay you 5% interest. What that means is every year, this 5% of $2 million is $100,000. So that means every year they're going to pay you $100,000. So basically, the idea is you keep the $2 million in the bank. They pay you $100,000 as like a thank you for you loaning them the $2 million. You live off the $100,000, so you don't spend more than $100,000 that year. The $2 million is still sitting in the bank, and at the end of the year, when you've done spending the $100,000, the bank is going to give you 5% again. They give you 5% every year, so they're going to give you another $100,000. So just by leaving the $2 million in the bank, they're going to pay you $100,000 per year if you just leave it, and you just live off just the interest. That's the idea. So then the $2 million never goes lower, and they keep giving you $100,000 every year. You can live like this forever, kind of thing. And then if you pass away, then your $2 million, you go to your kids or whatever you want to do, kind of thing. So you live off the interest. That's the idea. Now, if the interest rate is exactly 5% every year, you're going to make exactly $100,000 every year, and everything's great. But let's say the interest rate can change. So maybe 1 year they pay you 8%, then you're happy. You made $160,000 that year. They're going to pay you $160,000. You can live off that. But then the next year, let's say the interest rate is 2%. So they're only going to give you $40,000. You'd be like, oh crap, I'm used to living off $100,000. How am I going to live off of $40,000 this year? So that's a problem, okay? That's what they mean when they say we want the rate of return to be stable from year to year. So that whole story was so I can explain why we would want the rate of return to be stable from year to year. If it's 5% every year, then you're making $100,000 every year and you're going to be good. We don't want the rate, if it's going to change, we'd like it to go up so we make more money. We're scared that if it goes down, we're not going to be able to live off that money. That's the idea. And this example, they're not talking about a CD. They're talking about something else called a mutual fund. A mutual fund is basically, you've heard of stock market. You can pick a stock, A mutual fund is basically somebody who thinks they're smart, picks 20 to 30 stocks, and they give it a name, like Greg Miller's mutual fund, And then if you want to invest with me, think of, instead of putting your money in a CD, you're putting your money in my mutual fund. And I'm going to basically take your money, invest it in these 20 to 30 stocks. The idea is I don't know which one's going to go up, which one's going to go down, but I'm hoping on average that it's going to go up. And that's in general what the stock market does. It does go up on average about 10% a year, 8% a year, something like this. So, and then you could think of it like a CD, that you're going to make some money off your money every year and you're going to live off the interest. That's the idea. Okay, so instead of a CD, it's a mutual fund, but anyway, it's not that important. So what we want is we want the return rates to be stable. If they change every year, we don't want them to change a lot. Let's go ahead and keep reading. So now I'm reading from here. The investment manager invests with the goal of reducing volatility, which is year-to-year fluctuations in the return rates. So we don't want the return rates to change that much from year to year. Again, if it did change, we're hoping it goes up, but otherwise, but it's going to go down as well. So we don't want it to change that much so we can live off the interest. That's the idea. All right. So I don't care. So I'm measuring standard deviation. Standard deviation is what I care about. It's how spread out are the return rates. I want them all to be close together. Okay, so that's the idea. All right, let's keep reading. Following data represents the return rates in percent for mutual fund, for this guy's mutual fund for the past 12 years. The investor wants to estimate the standard deviation of the return rates for his mutual fund for all years. Okay, these numbers here are percentages, but I didn't put percent here on purpose because I don't want you to think it's a percent problem. This is a standard deviation problem. So I just left the percent symbol off. Think of the word percent as maybe like the units. It's not really units, but those are the units. This is 13.8%, 15.9%, okay? And this is this guy's mutual fund return rates for the last 12 years. I could find the standard deviation of those numbers, and actually it's given to you. It's 2.97 whatever percent. But what we want to know is the standard deviation of the return rates for all the years. So even though I have data for 12 years, this mutual fund might have existed for 80 years. So there might be 80 return rates. I want to know the standard deviation of all 80 return rates, but I don't have all 80. Think of those 80 return rates as like the population data. I don't have all 80, I have 12. So we're going to use the 12 that we have to estimate the standard deviation for the 80 return rates that we don't have. All right. Okay, let's go and do the parts of the problem then. So we are going to do the standard, what's the population sample, all that stuff, and then we'll build a confidence interval. What's the population? Okay, here's what the population is. I'm actually going to write down, sometimes in problems, it's hard to figure out what the population is. And I mentioned in another class that if you confuse population and population data, it's not a big mistake. So I'm going to actually write down what the population data is, but it's actually, you can think of it as the population. So this is the return rates, because I'm saying return rate, that's a number, so that sounds like population data. The return rates of this mutual fund for all years this mutual fund existed. So again, we might have created Greg Miller's mutual fund 80 years ago, which would be weird because I'm not 80, but anyway. And you take all 80 return rates, and that's the population. And so get the word all in there. Return rates of this mutual fund for all years the mutual fund existed. The sample is the 12 return rates that we have. Again, that's really sample data, but it's okay. The return rates of this mutual fund for the last 12 years. Okay, questions on this much? Okay. Population parameter, the symbol is sigma. No, read the problem carefully. The investor wants to estimate. If they say you want to estimate something, then that's an important sentence to read. Want to estimate the standard deviation. Boom, standard deviation problem, sigma problem. Or if the problem says build a confidence interval for standard deviation, then it's the sigma problem. Okay, so sigma. Now, when you describe sigma in words, the first thing you're going to write down is the standard deviation. And then remember, standard deviations can only be calculated from a group of numbers. You got to mention what group of numbers are we finding the standard deviation of? It's the standard deviation of the return rates of this mutual fund. Of the return rates of this mutual fund. But which ones? All of them. Mutual fund. Standard deviation of the return rates of this mutual fund for all years this mutual fund existed. So it's basically, I wrote standard deviation of, and this is the population data is what I wrote there, or population, whatever, same thing. In this problem, we're treating them like the same. Because otherwise, if you ask what's the population, it gets a little weird. Like, I don't know, all years? since the mutual fund existed. I don't know, it's weird. So again, if you confuse population and population data, it's not a big mistake. Sometimes it's fine. Okay, but anyway, it's a standard deviation of the return rates for all years this mutual fund existed. Okay, what's a sample statistic? S, it's a standard deviation of the return rates. Of which return rates? The last 12 return rates. So the standard deviation I'm just going to write down the sample of the return rates of this mutual fund for the last 12 years. Okay, now we got to calculate this. Sometimes they give you data and you have to calculate it. Other times they'll give you the answer. So the last problem we did, they gave us data, we had to calculate stuff. In this problem, I know the data's there, but pretend that they gave us the problem, like they gave us these numbers. So see, I have them written there. X bar 11.05 is the average of these. Like if you add them all up and divide by 12. This is the standard deviation of all these. If you find the standard deviation of those 12, that's what you get. So pretend that it's given to you. Now, one other thing I should mention to you, sometimes they'll give you information and try to throw you off. You don't need to know X bar for a problem in section 9.3, but you do need to know it for a problem in section 9.2. So in this problem, if they gave you this, it might confuse you. You might go, maybe it's a 9.2 problem, but it's not. It's a 9.3 problem because we want to estimate the standard deviation, but they gave you information you don't need. Once in a while, that's going to happen. So that's why I can't emphasize enough, read the problem super carefully. So I actually don't need this number 11.05 at all, but pretend it was given to you. But this is what I need. And I'm going to go to I'll just go ahead and write the whole thing. Okay, 2.97917. Okay. That's a little too many decimals. 2.9, I'm just going to go 2.97%. But I'm not going to write it as like that because you might think it's a percent problem. So I'm going to write it in words. You can totally write percent. I'm just trying to tell you we've done percent problems, and I don't want you to think when I put the percent symbol, this is a percent problem. It's not. It's a standard deviation problem. But think of each of the numbers as like having a units, and the units are percent. And since when we write percent, we usually go to 2 numbers after the decimal. I'll just go to 2.97. All right, questions on this much? Okay, part E then is saying guess sigma. We know S is the standard deviation of the return rates for the last 12 years. Here's what it is. What's the standard deviation for all years? I don't know. I'm guessing 2.97. This is how you write that. Sigma is approximately S, which equals 2.97%. If you write the percent symbol, it's totally fine. It's better as long as you don't get confused and think it's a percent problem. Okay, now we're going to go ahead and build a confidence interval. We don't like one number guesses. I'm guessing sigma is 2.97. I don't want a one number guess. I want an interval guess. That's what part F is. Find 95% confidence interval for the population parameter. All right, so here's how this is going to go. We need to find, again, chi-square left and chi-square right. In order to do that, you're going to write down alpha as 1 minus the confidence level. 1 minus 0.95, which is 0.05. Remember, confidence level is this percentage, right as a decimal. 1 minus that, 0.05. Then you divide it by 2. You always do alpha divided by 2. When you do that, you get 0.025. Then you can write down the degrees of freedom. Degrees of freedom is n minus 1. N is 12, so degrees of freedom in this problem is 11. Then you draw a picture. Picture goes like this. Okay, and then you label it chi-square distribution. You're going to put a tick mark on the left and label it chi-square left. And put a tick mark on the right, label it chi-square right. And then from both of those numbers, you're going to go up to the curve. You shade the ends. So shade to the left of chi-square left. So that, and then shade to the right of chi-square right. Each of those areas is this alpha over 2. So this area here is 0.025. And this area here is also 0.025. Now, the way the chi-square table works, you need to know the area to the right of the number you're looking for in order to find it. So this number will be easy to look up because I know the area to its right is 0.025. So we're going to look up that one first. Area to the right, 0.025. Degrees of freedom 11. Let's go to the chi-square table. Area to the right, 0.025. Degrees of freedom 11. And we got that 21.920 for that one. Okay, now to get chi-square left, that's a little bit extra work because I need to know the area to the right of a number in order to look it up. Okay, I know the area to the left of this number. I need to know the area to the right of it. So I'm talking about the area from this line here to the right forever. When I say to the right forever, I don't just mean the white unshaded part. I mean that plus this red. I need to know that area. The way you do it, you do 1 minus this. So that area there is 1 minus 0.025, which is 0.975. So the area to the right of this number is 0.975. So when you're finding chi-square left, you're going to have to do 1 minus this number. And that'll be the area to the right. You look for that as area to the right and degrees of freedom 11 in the table. So 0.975 is the area to the right. Let's go to this picture here. I mean to this table. So 0.975 is here. Degrees of freedom 11. And you go to the right like that, down like that. And we get 3.816. Okay, that's how you find chi-square left and chi-square right. But then after you find chi-square left, chi-square right, then you just plug into the formula to get your interval. Okay, let me go ahead and erase this. Okay, so, but I'll just remind you the answer. So chi-square left was 3.816. Chi-square right is 21.920. All right, and now we can build the interval. All right, so the formula for the interval is n minus 1 s squared over chi squared right square root. This one is n minus 1 s squared over chi squared left square root. All right, n again is 12 because there's 12 numbers in our data. So you put 12 minus 1 there. S, oh, I gotta go remember what S was. Okay, S was 2.97. Okay, this is gonna be 2.97 squared. And then here's chi square right, 21.920. Again, don't square, you never square the bottom number, even though it says square. It's the number in the table. So chi square right, the number was 21.920. Don't square it. Don't look at this and think you should square it. On the other side, same thing. It's going to be 12 minus 1. So the top is the same thing. 12 minus 1, 2.97 squared. Bottom chi squared left is 3.816. And then you calculate those things on the calculator. So let's see, 11 times 2.97 squared divided by 21.920, and then second root, second answer. I'm getting 2.10%. Again, you can write the percent symbol. It's up to you, but let me go ahead and leave it like that. The other one is 11 times 2.97 squared divided by 3.816, and then second root, second answer. And I'm getting 5.04%. And, oh, I'm writing the word, okay, so percent. So there's my interval. Just again, in this section, think of it as when you write, since it's an interval for sigma, think there's going to be units here, okay? Because the because return rates are in percent, I'm thinking of it as units. Okay, so there's my interval. This is not the return rate or the average return rate. This is the standard deviation. The standard deviation is somewhere between 2 and 5%, and this number here, these numbers are giving me an idea of how spread out the return rates are, or how consistent the return rates are. Okay, we're done with part F. Any questions on part F? All right, sounds good. I'm going to go ahead and skip part G because, you know, we keep going over what does it mean. So you know how to do that, so I'll skip that. Let's go to part H again. Like in example 1, they're saying, okay, now that you built the interval, let's answer a question. The interval is supposed to give me useful information. It's going to be useful in answering this question. The investment manager wants to have a population standard deviation, that's sigma, below 6%. Does the confidence interval validate this desire? Below 6%. Remember, we want the standard deviation to be small to be if we want consistency. That's our goal, right? We want high consistency, so we want a low standard deviation. And this guy is saying as long as the standard deviation is less than 6%, we're happy. It's low enough and we're happy. Does the confidence interval validate this desire? Now, our confidence interval, just to remind you what it was 2.10%. On that side, and this side is 5.04%. Let me read the question again. The investment manager wants to have a population standard deviation for the return rate below 6%. Does the confidence interval validate this desire? What do you guys think? Yes or no?
Yes, it does validate.
So the answer is yes, because, again, if you're going to write something, what would you write? If you believe the interval that sigma is between 2 whatever percent and 5 whatever percent, so you're believing sigma somewhere between there, then it's definitely below 6% because all these numbers are below 6%. Okay, so that's basically the idea. Again, I don't want to say much more than that. I'll let you write it out in words on your own. But our confidence interval, well, we want sigma to be less than 6%. So we want sigma in the green region. And we're saying that we think sigma is between 2.10 and 5.04. We believe that sigma is in the red region. So if sigma is in the red region, it's definitely less than 6%. That's what's going on there. All right, so the answer is yes. So we're happy, you know, it's consistent enough for us, this mutual fund. That's the idea. All right, that's example 2. Any questions on example 2? One last thing about this. So in this problem, like I said, the standard deviation was given to you. So I already mentioned to you that you don't ever square down here. You're never squaring anything. Chi-square right is a number off the table. Chi-square left is a number off the table. But I want to take a look at the top for a second. That is a power of 2. But they could be tricky, and this may not ever happen to you, but I just want to mention it just in case it happens. They could be tricky depending on what they give you, okay? If they give you data, like example 1, we don't have to worry about this, but in this example, they gave us S. If S is given, you're going to have to square it. So if the problem says we have data, we calculate the standard deviation of the numbers in the data, and S is, you know, and the standard deviation is whatever it is, you're going to have to square it. But here's one way they can word the problem to try to trick you. They could say, we had data, we collected data, and we calculated the variance of the data, and the variance is this number. So only in that situation, if they say we collected data, we calculated the variance, and the variance is like 1.7, then you're not going to square it, because if they say they calculate the variance, they found S squared. So if they find S squared, then you don't square it. They've already kind of squared it for you. Okay. So the top where it says S squared, sometimes you square, sometimes you don't. If you know S, you need to square it. Okay. But if the problem words it that way, where we collected data, we calculated the variance of the data, then that means they calculated S squared. It's like they already squared it. So then you just put that number in here and you don't square it. The bottom, on the other hand, you never square it. Okay, study super hard. See you next class.